Okay, all right. So I was just saying that my talk
Recording
will
in progress.
discuss. We'll discuss the ALICE 3, which is the phase of the ALICE experiment planned for the next decade, which aims at advancing the boundaries in the QGP studies at the LHC. And we'll discuss the scientific and technological challenges. And I would like to start with a brief introduction, just to put it in context. So this is the only part where I will be a bit pedagogic, and then the rest will be a bit more technical. But just to remind everyone that at the LHC, at CERN, you see here an aerial picture of the LHC near Geneva. That's the Lake of Geneva, the airport, and along the 27 kilometers long ring, you see the four main experiments. So the LHC collides protons usually, but it also smashes together the nuclei of heavy atoms. Primarily lead nuclei so far, and it does so for about 1 month every year, and for a very good reasons. That is creating a plasma of strongly interacting matter to study the fundamental properties of QCD at the highest energy densities. And these collisions are presently studied by all four main experiments. So originally, the ALICE detector was designed and optimized to study heavy ion collisions at the LHC, but then it became clear pretty soon that also the general purpose experiments, ATLAS and CMS, and more recently also LHCb, have a very good performance in measuring these nuclear collisions, which are characterized by a very large multiplicity of particles. In a nutshell, the main scientific objective is to understand how the macroscopic properties of the high-density QCD matter, which involves many degrees of freedom, are connected or emerge from the microscopic laws of strong interaction. Now, given that indeed the one following this seminar is quite familiar with these topics, I will be here very brief. It's just a very quick reminder that one of the distinctive features of the strong interaction is the asymptotic freedom. So the fact that the interaction between particles becomes weaker when the momentum exchange of the interacting particles is large, or alternatively when considering short distance interactions. So as a consequence, the coupling constant so depends on the momentum scale of the interaction. And for processes involving large momentum transfer between quarks and gluons, the calculations then can be addressed via a perturbative approach, right? Where we involve an expansion to higher orders in the strong coupling constant. While when moving to interactions involving low momentum processes, also when we try to describe the properties of a system which consists of a relatively large number of strong interacting particles, the perturbative QCD cannot be used. On the other hand, this is the regime of QCD, which is particularly important because it's exactly at that regime that the phenomenon of confinement is observed. So the fact that quarks and gluons cannot be isolated. So, and when studying, as we know, spatially extended ensembles of quarks and gluons, we also refer to it as a QCD condensed matter. So when studying this, or the study of this, has revealed that when heating a system of this type of strongly interacting matter with zero net baryon density to a temperature which exceeds a value of around 150, 160 MeV, so this brings to the creation of a quark-gluon plasma. So a state of matter where the two of the basic features of low temperature QCD, which I was mentioning, so the confinement and the chiral symmetry breaking, so essentially are not present anymore. And in this regime plays an important, crucial role among the theoretical approaches, the lattice QCD. But then the continuous space-time is discretized on a lattice. And lattice QCD provides a numerical approach, so essentially based on QCD, for solving static problems in this non-perturbative domain. And once the equation of state of QCD matter is numerically evaluated with the lattice QCD, then we can extract the temperature dependence of various thermodynamic quantities, such as the pressure, the energy density, or the entropy density. And the main result of such calculations show that a strongly interacting system with zero net baryon density evolves smoothly from a confined, so hadronic state toward a deconfined partonic state without a singular behavior, when the temperature is increased above a value of 155 MeV. And because of this smooth evolution and the absence of the real phase transition, this is indicated as the pseudo-critical temperature. And the liberation of the many degrees of freedom when moving from an hadronic state, where the degrees of freedom are the hadrons, to a partonic state, is indeed marked, as we can see here, by this very dramatic increase of the energy density, for instance, here normalized to the first power of the temperature. Now, let me just remark as a last comment on this plot that the even at temperatures of 400 degrees, these are essentially the highest temperatures we achieve in nuclear collisions at the laboratory, or in the ballpark of the temperatures we reach in the laboratory. The energy density is still 20% lower than the non-interacting ideal gas limit, which should be reached when at a very large temperature due to the asymptotic freedom. So, and this residual difference has, as we know, profound consequences on the properties of the medium which is created, with this remaining coupling, which gives to this medium very specific features. Essentially, as we know, the QGP manifests itself as essentially an almost a perfect liquid, and not an ideal gas, with the presence of bound states of quasi-particles, quark-quark, gluon-gluon, or quark-gluon. And for this reason, we refer to this state as a strongly coupled QGP or SQGP. All right, so, and the scientific mission of the ALICE is to characterize the physical properties of this state of matter, and which is the state of matter which is conjectured to have existed also in the first instance of the Big Bang, based on considerations of the temperature evolution of the universe. and is also a state of the matter, well, it's also conjectured that may still exist at the core of the neutron stars, but it's the state of matter which can be created at the laboratory with the collision at relativistic energies of heavy nuclei, where temperatures well above, or energy densities well above the critical value can be achieved. And well, this is, you're all very familiar with this type of schematic representation of the evolution of the collision, starting from the two Lorentz contracted disk representing the two lead nuclei accelerated in opposite direction. The instant where they go through each other, so they penetrate through each other. So the hard scattering, the formation of a system which quickly equilibrates and expands. Where particles then have a collective flow, so the system becomes more and more diluted, the temperature drops, and then we have first a chemical freeze out when hadrons form again, so where the partons recombine to form hadrons. They continue to interact till a certain point the system is so diluted that there is no momentum exchange anymore, and then the kinetic freeze out, and then the particles fly out in all possible direction, reaching our detectors. And the obvious question is whether these collisions can indeed realize the conditions for the formation of a deconfined state of matter, where lattice QCD projects to be formed at values exceeding an energy density of 0.42 GeV per cubic Fermi, or a temperature of 156.5 MeV. And now when we collide heavy nuclei, so the idea is that indeed we have the possibility of concentrating in a very small volume a very large amount of energy with the multiple, almost simultaneous nucleon-nucleon collisions. We can control and vary the energy deposited in the collision by varying the collision system and geometry, so the impact parameters. So whether they are head-on collisions or the center of the two nuclei is slightly offset. And of course, I mean, we don't have a direct observation of the QGP, but we rely on the emerging particles as probes of the state of matter, which has led to their generation and imprinted the basic features. All right, and to do that, a comprehensive study actually entails the study not only of heavy nuclei collision, the collision of heavy nuclei, but also to disentangle effects that are not related to the formation of quark-gluon plasma, called the nuclear matter effect. We also study proton-lead and proton-proton collisions, and as well as it's very important to study collisions with the different species. And for instance, we studied already xenon a few years ago, and oxygen is planned for next year. And now it is not my intention, it's outside of the scope of this talk, now to review the many results published by Alice, but just let me answer the first question. Do we realize the conditions for the formation of a quark-gluon plasma? And the answer is yes. Essentially, although, I mean, we still have to rely to extract the basic features on ad hoc models, but let's say we have quite a strong indication that the energy density of the system generated in the nuclear collisions that you can see here in this plot. So what is measured is the energy density times tau zero, so the formation of the equilibrated system. So we can infer an energy density, assuming a tau zero of 1 Fermi over C, of 12.3 GeV per cubic Fermi. which is well above the critical energy density value, or by measuring the inverse slope of the distribution of the spectrum of thermal radiation. We can measure an effective temperature of the thermal of the system throughout its evolution, and this is of the order of 300 MeV. We also measured the lifetime of the system, which is of the order of 10-15 Fermi. Now, altogether, Alice has published 440 papers, which present a quite wideband exploration of the QGP features, including, for instance, the first measurement of the mass dependence of in medium energy loss, the discovery of a new regime for the formation of charmonium production. So we have a clear evidence that hadrons which are producing the initial hard scattering and that they are completely melt in the very hot system, and then they can be regenerated by recombining partons produce so uncorrelated partons. We also discovered the collective effects in proton-lead and lead collisions, but also we carried out many other measurements which go beyond the scope of characterizing the QGP, as for instance, a systematic study of strong interaction among nearly almost pair of stable and unstable hadrons, or a pure study of QCD, including, for instance, the first direct observation of the Dedekind effect in QCD by studying PP collisions, or also more recently the first measurement of the anti-helium-3 in matter, and the impact on the transparency, on inferring the transparency of the galaxy, so the propagation of anti-helium-3 in the interstellar space. And this is very important, is instrumental to the quest of dark matter by AMS. Now, we last year in July, we have also published sort of a review paper with a selection of the ALEX physics results and a discussion of their implications on the current understanding of the QGP, and that is a good reference to see all the many results. But now let me move to the future. So, and this is really a bit the far future. The ALICE is running since 10 years. So we went through the so-called Run 1 and Run 2. The Run 2 was completed in 2018. Then in the period of 2019 and 2021, we had a 3-year long shutdown of the LHC. And during that phase, we have had upgrades of the machine and of the experiment. We are now in the course of Run 3, which will be completed by 2025, followed by again by a 3-year shutdown of the LHC to essentially complete a very important upgrade of the machine and really enter in a new era of high luminosity, and also upgrade of the Atlas and CMS experiments. And then there are 2 years of shutdown in 2033 and 2034, but then ALICE and LHCb plan to install respectively 2 new detectors, which we refer to as ALICE 3 and LHCb 2. So these are also called the phase 2B upgrades. And then we will enter into a new phase of about 10 years with 2 runs, Run 5 and Run 6, all the way till 2041, 2042, which should complete the operation of the high luminosity program and of the LHC. And now let me remark that, of course, making progress in our studies rely on one hand, on increasing the statistical significance of our measurements, so by increasing the sample of collisions that are available to study our observables. And on the other hand, so these are the two pillars, on the other hand, it also relies on improving the performance of each individual measurement, so the performance of our detectors. And you see, it's quite nice to see how over time, for instance, the luminosity, so the rate of collisions is projected to increase. You see here in blue, the luminosity for PP collisions measured in integrated luminosity in inverse femtobarn. And in yellow, you see the luminosity for nuclear collisions, but what I'm showing here is nuclear luminosity, and it measured in inverse picobarn. So you see that they follow up quite a dramatic increase over time. Now coming to Alice. Alice had a major upgrade of its detector during the long shutdown 2. And so this new detector, which will be operated now for during this decade, with essentially an increase in the rate capabilities by nearly 2 orders of magnitudes. So we were limited in run 1 and run 2 at about 1 kilohertz. So 1,000 collisions per second fully recorded on tape, and we will go to rates of in excess of 50 kilohertz. And more, equally important is the major upgrade of the detectors, where we install a completely new silicon tracker with a much enhanced performance in terms of determining the point in space where the particles are originated, so the primary vertex and the displaced vertices of short-lived particles, and also a very important upgrade of the time projection chamber to allow to have a continuous readout of the detector, overcoming the limitations of that we had in the previous decade. Now, this is a very interesting plot because it shows, by taking, of course, these are just 2 figures of merit. We could have taken many others, but 2 very important ones. So you see here the point in resolution, and here is the acceptance times the interaction rate. And you see how at each upgrade, at each phase, we are improving either on both on one of these 2 parameters, and altogether going from the first detector to the one we are preparing for the next decade, there is really an improvement in measuring the impact parameter of particles by by a factor actually of 20, and a dramatic increase of 2 orders of magnitude, even more, a few times, a few hundreds on the rate capability. So this is really a big deal. Now let me tell you what we envision for this new phase, Alice 3, which is the detector, a next generation detector for the 30s. But first of all, what we aim in terms of key physics questions and key physics drivers. What we expect is still to be the big questions unanswered by the end of this decade. So we believe that still there will be the need of new observables and higher precision to completely understand the nature of the interactions with the quark-gluon plasma of highly energetic quarks and gluons. So really to develop a detailed macroscopic picture of the interaction of energetic quarks and gluons with the QGP. So the ultimate goal would be really to have indeed the measurement, the detailed momentum and temperature dependence of the diffusion coefficients, and as I said, really detailed macroscopic description of the interaction throughout the evolution of the system. Now, another big question is, to what extent do quarks of different mass reach thermal equilibrium? We have seen and established that charm is to a very large extent equilibrates in the QGP. Does also the beauty quark behave in a similar way? So this would be a very important question. So going really from the interaction with the medium to the full equilibration or partial equilibration, and then how fully equilibrated or partially equilibrated hadrons can recombine to form hadrons. So what are the mechanisms of hadron formation in the QCD? And these three questions will be addressed by systematic measurement of multi-charm and beauty hadrons. So the production yields, but of course also the flow of multi-charm and beauty hadrons. Another important part of the program regards the measurement of the QGP temperature throughout this space-time evolution and the mechanism of a chiral symmetry restoration in the QGP. And for that, we aim at very high precision measurement of the leptons. Of course, this is also an area on which efforts have been made, tremendous efforts have been made in the past 20, even more years. But we really believe that we are reaching the required precision to really have a quantum leap in understanding and measuring these observables. And there is much more. So we have also the measurement of the fluctuations of conserved charges to have a more systematic study of the QCD chiral phase structure. We will continue our measurement of the hadron, of the measurement of the interaction at short-range interaction potential of hadrons, the formation of nuclei and hypernuclei, and much more. And I would like to refer you to the letter of intent that we have published last year. Now, to do all that, we need a completely new detector, essentially, which is optimized for high efficiency for the reconstruction of multi-heavy flavor hadrons and of low mass dielectrons. Okay, so these are the key drivers. As I said, the program is much broader, but when developing the detector layout and concept, these were the two main drivers. Okay, and I will show this a little bit, but essentially all this calls for unprecedented precision in the measurement of the primary secondary vertices. So with the vertex in detector very close to the beam, and with unprecedentedly low material budget, we have to have a very robust particle identification for muons, electrons, photons, and hadrons over the full detector acceptance. And with respect to the detector, we are operating throughout these two runs, run 3 and run 4. So with respect to Alice 2, Alice 3 will yield an improvement in the vertex precision by another factor of 3, reaching a precision of 10 microns for particles at 200 as low, with a momentum as low as 200 MeV. A very important increase of the acceptance of the detector by a factor of 4.5. So this is a detector which has a very large rapidity coverage with 8 rapidity units. And again, another important improvement in terms of rate capabilities, another factor 5 for nuclear collisions, for heavy ions, and even a factor 25 for PP collisions. And all this is based on novel technologies. You will see that there is a massive employment of the silicon detectors, really in a very modern in a very modern fashion. Okay, let me just before moving to the detector part, just make a few examples why all this is required, and start with the multi-heavy quark physics, starting with the goal of understanding, for instance, the hadron formation. Now, we know that in heavy ions, so the multi-charm hadrons, essentially produced completely only in processes that combine charmed quarks, which are produced in independent parton scatterings. And therefore, this fact that, you know, they can essentially be formed only with this mechanism opens a direct window on the hadron formation from a deconfined QGP. Is really the ideal probe, because that allows to set unique constraints on the hadronization mechanism, which go beyond the in-vacuum fragmentation, and so can provide really unique constraints on the connection between the hadronization and also in the degree of equilibration in the QGP. Okay, so that is what is really important. And indeed, enhancement are expected by as much as, and here I'm listing some of the studies to which we have made reference to, so mostly thermal models. Enhancement are expected by as much as a factor of 100 for the recently observed XICC, when we go from proton collisions to heavy ion collisions, even as much as a factor of 1,000 for the yet undiscovered omega CCC baryons. So this is a really very large dynamic range, dramatic values, and therefore the observation and precise quantification of such effects would really represent a quantum jump for the study of the properties of the confined matter. And you see here our projections for the measurement of the XICC, for instance, with the Alice 3 detector. Here the plot is showing two different analysis techniques, standard analysis with rectangular cuts, and then using machine learning techniques. But you see that essentially we're able to have a good measurement all the way down to 0 PT for an integrated luminosity of 35 inverse nanobarn, which is what we expect. One of the crucial I can say aspects of this measurement is really the ability of the detector to actually reconstruct or have a direct measurement of the strange baryons involved in the decay chain. So you see, we start here from the XICC, which decays in XIC and one pion. Then the XIC goes in the Xi minus, for instance, in 2 pions. And here already we measure directly the Xi minus, and then the Xi minus, which decays in a lambda and a kaon. And then we have the further decay of the lambda in a proton and pion. So the fact that we have the direct reconstruction of these particles is what really gives a tremendous I can say enhancement of these measurements. And all this, however, requires to have vertex detectors which go as close as to the interaction point as 0.5 centimeters. So we need to go as close as 5 millimeters to the interaction point. So let me make another example. Another area where Alice 3 will enable a significant progress is the study of correlations of heavy quark, for instance, of heavy quarks. So to study heavy quark energy loss and equilibration in the QGP. And in particular, we studied now in the context of this letter of intent, the D0 bar correlation. Now, the heavy flavor correlations will allow, indeed, providing, again, an unprecedented constraints on the effect of the interaction with the medium and on the transverse propagation of the F quarks in the medium. Essentially, what we do, we try to observe the degree of decorrelation of the CC bar pairs in the medium. And by doing that, we can get a direct indication of the degree of equilibration of the charm quarks in the QGP, right? So in the sense that we start with the distribution in the absence of equilibration, we know what the distribution should be, with a peak for the back-to-back CC bar pairs and another peak for the collinear CC bar from gluon splitting, and then in the limit, let's say, of full equilibration, so the flight line of the charm quarks, of the back-to-back charm quarks, would be fully randomized, and so there should be no remnant of the initial correlations would be visible. So then one would expect a completely flat line and not anymore such a distribution, okay? And so this is also a measurement that is not possible with ALICE 2, but is possible with ALICE 3. I actually thought that, well, you see here which accuracy we expect on the measurement of these DD bar correlations. I've not forgotten to put a plot with the projections for the measurements during this decade, but essentially we do not achieve the required precision. The errors are simply too large. And now moving to another topic is the high precision measurement of the low mass dielectrons. So the temperature of the QGP can be extracted, it can be accessed by measuring the yield of thermal dielectrons that are emitted by the plasma and escape the collision zone essentially unaffected, and so they deliver really information on the QGP conditions at early times and throughout the evolution of the system. Now, the temperature can be inferred from the dielectron excess in the intermediate mass region between the phi and the j psi masses. So the idea is that the inverse slope of the invariant mass spectrum provides a Lorentz invariant temperature that is essentially insensitive to the expansion of the medium. And therefore, it's a true measurement of the average temperature. Of course, after the subtraction of the background, which is coming mostly from the electrons from semi-leptonic decays of heavy flavor hadrons, which are really produced very abundantly at the NHC energies, and that makes it the measurement particularly challenging. But also the pi-0 Dulles decays and also photon conversion. So we have a very large background, and in order to have these measurements carried out with enough accuracy, we need to have very precise measurements of these various background sources, which is what we believe we can achieve with ALICE 3. Already with ALICE 2, we will have quite a good measurement. Let me outline that indeed, while the saturation in the chemical freeze out, so after and at the hadronization has been essentially established experimentally during run 1 and 2, we still have to prove that the QGP temperature in the early phase so the t-slope keeps increasing as square root of S. And after the LHC run 3 and run 4, by the end of run 4 of this decade, we believe we have measured the average temperature of the QGP. So we have a measurement here. You see our predictions at the end of run 4. But we will not have access to a fine-grained picture of the temperature throughout the fireball time evolution. Okay, again, we have an average measurement of the temperature. And this temperature evolution will become possible only with ALICE 3, performing a measurement of the PT dependence of the lepton spectrum inverse slope. So we take really slices for different PT intervals. And you see here a projection, what we expect to have with the concurrent measurement of with the measurement of the spectrum at different PT intervals. Then also the measurement of flow will provide additional information also on the lepton time evolution. Okay, now, but the leptons can also be used to study the immediate modification of the spectral functions of the vector and axial vector mesons, and an ambiguous way to observe chiral symmetry restoration would be to measure the chiral mixing of the rho and its chiral partner A1, and this figure shows the expected impact of the rho A1 mixing on the thermal lepton of spectrum at the LHC energies. And although it is really a small effect, as you can see here, the mixing leads to an enhancement of the yield of the level of 15–20%. And so if we have a measurement of the spectrum with an accuracy of 5%, this will become accessible. So this is really a very difficult measurement, but we believe to have enough precision to have access with the required accuracy to a possible access in this region. Okay, so sorry. All right. Now all this requires the 4 detectors with unprecedented precision. And let me now, in the remaining time, just give you a few highlights. One of the important components is the tracker, the outer tracker. I've mentioned already how important it is for both low-mass leptons and multi-charm hadrons to have very high precision in the measurement of particles at low PT and in the measurement of the impact parameter of these particles. And in order to achieve the required precision, we aim at building a detector with a very large rapidity coverage. Why? This is particularly important for the d-bar correlations. They have very large acceptance, is extremely important. And so our tracker is a full pixel detector, will be by far the largest pixel detector ever built. Already ALICE has installed the largest pixel detector ever built. This will be larger by another factor of 10 with the 60 square meters of silicon pixel detectors based on the most modern CMOS active pixel sensor technology, featuring a spatial resolution of 5 microns, essentially in the 3 dimensions, okay, on the plane of each barrel layer, but also in the radial direction, with an extremely low material budget. The full integrated material budget of the full tracker is below 10% of X0. and a very low power density. And here the key component is this CMOS technology that Alice has pioneered.
Sorry, Luciano, probably this, I don't know if it's only me or the slide is still on 22 page.
Sorry. Is it 23 now?
Yeah, now it's okay. Thank you. Yeah, please.
Okay. All right. Apologies for that. So anyway, the key component is this CMOS sensor, which is a novel development pioneered by Alice. I don't want to become too technical, but still let me explain very briefly. So this is essentially like a standard chip, okay? CMOS chip as the CMOS, using the CMOS technology used for the fabrication of, I don't know, a microcontroller or a CPU, with a few basic features, and in particular, essentially the charge collection electrode. So the sensitive volume is a high resistivity silicon layer. So on top of the standard substrate of a CMOS chip, for instance, the CMOS used for a CPU, it is grown epitaxially a high resistivity layer. The high resistivity of the silicon is extremely important. And then the element to collect the charge is an NP junction. So we have an N-well. So this is exactly the type of structure that is used also to implement, for instance, a PMOS transistor. You see here it's an N-well. And then the N with the P type of silicon underneath form a diode. So it creates a depleted volume underneath. So where there is electric field, we can vary the size of the depleted volume to make it essentially fully depleted, actually the full sensitive layer, such that we can collect the charge generated by ionization by the crossing particles. So it liberates electron holes, which then are trapped in this volume here. At the barrier, at the interface with all the surrounding structures, there is an electric field which pushes back the ionization charge. So we create like a silicon chamber, if you want. And then this charge is immediately collected by drift, or it wanders by diffusion until it reaches the depleted volume, and then is collected by the charge collection electrode, okay? And so that is a technology we successfully developed for the ALICE, for the ITS2. The same technology is now being used also by S-Phoenix. Actually, the detector was put in operation probably last week, if everything went fine. And so it's really a very novel technology. Now, let me say just a few words about what I consider personally a very important aspect of this technology, and that also what could become more and more relevant in the future. The charge collection electrodes, so the pixels, each of these pixels has a size of 20, 30 microns, okay? So the pixel pitch. So you can imagine this as a little cubic volume of about 20 microns in the three directions. On the plane, but also vertically, we have about a sensitive depths of 20 micron. The charge collection electrode itself is an extremely tiny structure, actually of 2 by 2. We are making them even smaller. So featuring a very, very small capacitance. And the capacitance is so small, and you see here some of the measured values when we increase the voltage that we apply. So it goes down to essentially femtofarad values, okay? For a comparison, a silicon strip capacitance is 10 picofarad. For a standard hybrid pixel detector is 300 femtofarad. Here we're talking about 1 femtofarad, which means that this amplitude of the signal is the charge divided by the capacitance. So even if you have a very tiny signal of a few hundreds of electrons liberated in the sensitive volume, this still produces over such a small capacitance a huge signal, a signal without any amplification of a few hundred millivolts. So we are really close to entering a regime where essentially we produce a digital signal nearly without the need of any analog amplification anymore. And this we have very, very tremendous implications for the next generation of silicon detectors we can build. I think I can skip this slide. I've tried to put a few explanations how one can achieve a fully depleted layer. We started with partially depleted detectors, which work perfectly well. They have a very large charge collection efficiency, very high spatial resolution. They have the drawback to not be enough radar if we want to really put them very, very close to the interaction point. I mean, it would be impossible to put them at 5 millimeters from the interaction point. And if we want to go that close to the interaction point, we need to reach to have detectors which can withstand a neutron fluency up to 10 to the 15 or above that, 10 to the 16. And for that, we need to have full depletion in order to collect the charge very rapidly in a few tenths of picoseconds. And that makes it much less sensitive also to trapping mechanisms, and also concentrate all the charge in a single pixel. Okay. And anyway, this is there for your reference. There are references to the papers with which we have modified the processes to achieve the full depletion. Now the question is, how do you go that close to the interaction point? And that indeed requires another completely novel scheme for a barrel configuration. Many of you know that LHCb, which has however a forward type of configuration, has put a vertex detector, the so-called velo detectors, vertex locator inside the vacuum chamber. But in a barrel configuration, this is extremely challenging because essentially you have to put it inside a beam pipe, and you have to have a mechanism to open up the detector and close it around the interaction point. So you have to open it up and bring it to a distance of 10 millimeters or even larger when the beam is being injected and the emittance of the beam is large. And then once the beam is squeezed and is at the top energy, and then the emittance is much smaller, then we can close it around. And all this has to be done with a mechanics which is all contained within a very small volume. At the LHCb, there is the advantage that there is enough room all around to put the mechanics to move the detector in and out. And that is done with really a concept which we call iris, where the detector are sort of rotary petals in the secondary vacuum of the beam pipe. And with this, we will be able to achieve a point in resolution of a few microns at 1 GeV over C, and still keep a precision of 30 micron for particles with a momentum as low as 100 MeV. Now, let me mention that 40 years ago, Bjorken, in his famous paper on the XICC and omega CCC measurements, was indeed arguing that my guess for the resolution required is ideally a few microns in the transverse direction, okay? And perhaps it was saying 200 microns in the longitudinal. Well, it's nice to see that it was pretty right. That is what is actually needed, and 40 years ago, the technology allows to do that. And the precision would be of a few microns actually also in the longitudinal direction. Now, this is the technology we are using. Essentially, we have sensors which are as large as the entire wafer. That also entails a new technique called stitching, which allows to build circuits which are larger than the field of view of the lithographic process. And then these sensors are thin to very low values, and they can be curved around the beam line, as you can see in this picture here. and then kept in position by carbon foam, which has essentially a radiation length close to the one of air, and without any active cooling, but simply well, essentially we have to have the heat conducted towards the edges, where then we have indeed active cooling. Okay, all right. Now I don't have time because my time is over. I was planning to say also a few words about the time of flight detector, but also we envision, we have started actually a novel development, which is a CMOS implementation of the LGAD. So the idea is to have, again, a CMOS sensor fully integrated, including the readout electronics in a single chip with a time resolution better than 20 picosecond. And also I would have liked to say a few words about our REACH detector, which is based on aerogel and silicon PMs, but in particular with a projective type of geometry. But in particular, let me, although I don't have the time, say that what we are targeting here is, and for the first time, is the combination of the REACH detector and the time of flight in a single technology, by essentially having in front of the photon detector a silicon dioxide layer, which acts as a second layer to produce a Cherenkov light and distribute the photons of the Cherenkov light over multiple sands, such that then the time resolution is the time resolution resulting from many measurements in different sands. And so with this technique, we can measure the Cherenkov ring, but also we can measure the time resolution of the minimum ionizing particle crossing the photon detector. All right, and I think I can then stop here, concluding by saying that ALICE 3 will enable new avenues to access the fundamental properties of QGP and the dynamics of its constituents. It will also try to show that this will give access to the confinement, the Carré symmetry restoration, the mechanism of hadron formation, how the QGP properties are connected to the dynamics of its constituents, but also opens other new physics opportunities in other areas. And all this is based on innovative detector technologies, building on experience with the technologies already pioneered in ALICE, nevertheless require a very aggressive R&D phase in several strategic areas. And all this is also relevant with, for other high energy physics and nuclear physics facilities which are planned in different places worldwide. Thank you.
Okay, thank you very much, Luciano. So we highly appreciate this very excellent talk, and from the detector standpoint, which is also very inspiring for the outlook for the future about ALICE, and also in China. Yeah, here our ALICE colleagues also very eager to contribute and to learn and to collaborate. So let's see, yeah, if we have any questions, I believe. So, okay, yeah, just feel free to raise your hand or you write down the question in the chat box. So first, Xiaoming, please.
Okay, thanks, Luciano. Thanks very much for the very nice talk and very comprehensive conclusion of the roadmap. And I actually have two questions related to the ALICE 3. So the first question is that you introduced the dilepton physics in ALICE 3. Of course, they are very interesting. And actually, to do so, we also need the high precision of the electron PID, especially at no PT region. So I want to ask with ALICE 3, how we can improve the electron PID, and what is like the estimation of the compatibility of the electron PID in ALICE 3. Then I have a second question. Should I ask together or?
Yeah, go ahead. Go ahead.
Okay. Okay, so my second question is just a curiosity. So with ALICE 3, as you introduced that we will have the vertex, like the first layer of the vertex detector very close to the interaction point, like inside the beam pipe. We know that at the present we have like a type of background that comes from the beam induced background. And if we put the detector inside the beam pipe, whether it will induce like extra contamination for such kind of background. Okay, thanks. This often.
Thank you, Shamin. Both are very, very pertinent, relevant questions. Okay, so let me start with the question of PID. Indeed, you're completely right. The measurement of the electrons require a very robust electron identification with a very high purity. And that's why there is really a very important effort. So you see, we plan to have an inner top, an outer top, but they have a very, let's say, poor performance for electron identification, or at least this drops very, very quickly above 500 MeV. And for the measurement of the low mass electrons, we needed to have a good electron identification with high purity all the way up to 2 GeV at least, right? I mean, we have to go the intermediate masses. Ideally, if we want to really measure the temperature at pre-equilibrium, we would like to go even to 3 GeV. Okay, and so for that reason, the rich detector is really essential. Now the question is, what is the performance? So now let me see if I have a plot here. Was more showing the combination of the two. Okay, all right. So this is what we expect in terms of PID purity with the combination of the top and the Cherenkov detector using aerogel as a radiator. Okay, and you see that then we would be able to cover with reasonable purity all the way up to close to 2 GeV. Okay, but now what we are studying is a way of extending the electron identification by actually combining the aerogel with also a gaseous radiator with a very low refractive index. So you would have the aerogel, which has a refractive index, did I put it somewhere, 1.03, and this is 1.0006. And you see in this case, then we would be able to extend the electron identification, make it much more robust and extend it all the way above 4 GeV. Now we have to see now technically how this is feasible and et cetera, but indeed, precisely for the reasons you mentioned, I believe this would be extremely important. All the performance studies we have in the LOI, however, they rely on this performance that I'm showing in this slide, page 35. Okay. Now, coming to your second question, indeed, you're completely right. When we go close to the interaction point, and so we are at 5 millimeters. So indeed, the QAD interaction between the two beams, okay, which goes essentially, I don't want to quote wrong numbers, but this really grows very quickly with the intensity of the beam. I think it was the force power, probably even larger than the intensity of the beam. is really dominating when you go to those radii. And indeed, for this reason, this was one of the first aspects we've been looking at already for the ITS-3, but even more for this. And so in our simulations, we have included the background coming from the QED, electrons. And so the occupancies that we measured, and in this case, are still at the level of 1% or so. And we know by experience that operating a pixel detector with a high granularity with an occupancy at the percent level, we are in a comfortable region. But it will be a dominating component with respect to the particles generated in the hadronic collisions of the two beams.
Okay, thanks. So it seems that in both sides, at present, the performance is promising, right?
Yes. I mean, however, I mean, in particular for the PID, thanks for asking the question, because indeed it is also internally is something on which personally I'm trying to insist that we should really make an effort to try to further improve it with respect to the LOI values. So this will really go in the direction. I mean, you have seen this plots in particular for the chiral symmetry restoration. But we are dominated by other systematic errors here, okay, which is mostly the subtraction of charm. But still, these measurements they really will benefit from improving all experimental aspects of the measurement, in particular the PID.
Okay, thanks. Thank you very much.
Okay, just a following very quick naive question from my side. So there will be no like a forward detector like a MFT, because you just mentioned about the dilepton measurement. So in ALICE-3, there's no plan for something like a MFT, those forward things anymore.
No. Of course there is. What do you mean? So the tracker actually has a very large rapidity coverage. You see, it's not only the barrel, but also all of this. We go all the way to rapidity 4, including PID. Let me see if.
I see. Okay.
PID,
yeah, I didn't pay attention.
Oops. Okay, so the time of flight has also full coverage, as you can see, barrel and
I see. Okay, the forward.
but also the rich detector. Okay, so we won't have also the rich, because the time of flight in the forward direction due to the Lorentz boost as drops very quickly. But then we also have the rich detectors. And so we have now, if you are referring to measurements with the muons, because the MFT then is combined with an hadron absorber and the muon detector, a muon spectrometer. So in ALICE-3, we have a muon identifier, we have a hadron absorber, but only in the barrel direction. We were studying whether we should also put an end cap here. And then we have, you see, a hadron absorber, and then 2 layers of we are discussing either plastic scintillators, plastic tiles, or RPCs to measure, essentially to do muon identification, okay? And this, however, is mostly connected to the measurement of charmonia, botomonia.
Okay.
Maybe also it will be also interesting, although we did not carry out yet the studies, to look at the thermal radiation in the muon sector. But of course, here we only have access to relatively large PT due to the cutoff from the absorber.
Okay, thank you. So there's one question in the chat box. Can you see it? Then I don't. Is it possible to observe more heavier nuclei? So maybe detector-wise. Okay. Now you get me. I think
No, I have to look at that. If I'm not mistaken, we have a table with, I wouldn't need to check. I think we have a table, if I remember correctly, we go up to mass 6. Yeah, I have to look into that again. Yes, it should be possible. And the anti-hyperhydrogen 4 as well. But let me come back to you. So there is Kaisha. Okay, yeah.
Okay, then that way, please.
Thanks, Luciano, very much for your very nice, very exciting talk. So especially for run 3, run 4, and edit 3. I have one about 2 small questions. One is how is the state of the heavy flavor correlation measurement for the current and for run 3 and run 4? So I remember you gave some expectation about the heavy flavor correlation measurement. Can you speak? Can you give?
Yeah. No, look, I mean, for the UPCs, for the ultra-peripheral collisions, we already expect now in run 3 and 4 already a big improvement, because essentially the fact that we have a continuous readout of the detector, we do not need to rely anymore on an external trigger. So essentially, we will be able to collect all the UPCs to have a very powerful selection means, because we do it essentially after the full reconstruction of the event. So already, I think already in the course of run 3, as soon as we start reconstructing the sample of the lead collisions, we will record in October and November this year. We will be able to really to show the superior performance of ALICE 2. And with ALICE 3, then the scheme is exactly the same, but of course with again an improved detector, so one would expect even higher quality measurements.
Oh, okay. Yeah, I have a lot of questions. Is about the for L3 plan. Is the current actually for Chinese group we are very interested in the track measurement, but we are organizing this kind of the application. Anyhow, it's not a application, but we provide some proposal to report the future plan to NSFC, and yeah, currently to this step. But in order to organize this further work, include the report and the proposal, so we would like to know how is the state of the for ALICE3, how is the state of the funding organization in ALICE corporation?
Okay, well, that's now you know this is precisely a process which is taking place now, which has started last year, but is really mostly done in the course of this year, namely preparing a document which has been requested by our committees, on one hand to show different scenarios for the implementation of the detector and the associated costs. Essentially, we have to defend the proposed detector layout versus the physics that this will enable. This is already in the LOI, but you know they would like more to see what happens if your magnet has a field of 1 Tesla instead of 2 Tesla, for instance. Okay, what happens to your physics performance if the tracker has a radius of 60 centimeters instead of 80 centimeters, and etc., etc. And so this is one aspect. And the other aspect is indeed to present a funding scenario. So essentially a realistic plan for the contributions from the different funding agencies from the different countries. And the approach that is being followed, as usual, is the one of a fair share funding scheme, where essentially each country or each group, community contributes with a share which is proportional to the number of scientific collaborators. Okay, so that is the scheme. And then, of course, there will be funding agencies hopefully providing a funding which exceeds the fair share, because maybe they are interested in developing a given technology or detector, and so they go beyond. That is also pretty much important. But let's say the reference is a bit as a fair share of the total cost.
Yes, thanks. I just actually China's group also provides two proposals. One is on the track, and another one is on the air guide, the machine. Yeah, so to focus on 83. Yes.
Yes, I mean
we will try to organize and further discussion about this on the 83 upgrade. Not the upgrade is the 83. Oh, okay, yeah.
Let me indeed remark that this technology, which I've been emphasizing, is the result of 10 years of R&D, where indeed the CCNU has played a very important role, also in the design of the sensor, then later in the construction of the detector. Since then, the Chinese collaboration in ALICE has grown significantly, and indeed as a collaboration, but also very personally, I'm very much looking forward again to have a very close collaboration on this very interesting and promising future that lies ahead of us.
Yeah, thank you, Luciano.
Okay, yes, thanks both the question and the answer. Okay, and the time actually is almost up, so yeah, we just we can let's appreciate Luciano again for this really nice talk and discussions to our Chinese allies, colleagues, and all the audience. So basically, we conclude today's seminar, and have a nice day.
Thank you very much for having me and for listening to me. Thank you very much.
Yeah, thank you. Bye-bye.
Bye-bye.